screen. All right. Just give me some second. Okay, so I want to be sure you can see my screen. Can you all see my screen?
Yes, we can.
All right, nice. All right. So I'll be talking about some things, and here is a very brief presentation of what I'll be discussing with you guys. So I want to talk about what is PyBullet, and I want to talk about what is ROS2. Why do you need PyBullet? As a robotics engineer, as a robotics developer, why do you need ROS2 as well? So we also want to talk about robot models, because when it comes to robotics, you're always dealing with something like hardware. And for you to be able to simulate, have a kind of simulation of your hardware, you need to be able to represent your robot model in a simulated environment. So that would take us to talking about URDF, which stands for Unified Robots Description Format. So it's just basically a way to describe how your robot looks like. All right, so then we talk about the installation, how you can install PyBullet. And I want to tell you guys, if you are still, if you're really into robotics, and you're still really maybe using the Windows operating system, I want to encourage you, try to move to the Linux operating system. It's going to help you a lot. So many things on Linux are not as complicated as the way you have it in the Windows side. Okay, so that's the PyBullet and the introduction to PyBullet. So we also see how you can use the PyBullet API. Basically, when we say PyBullet, we're just talking about an API, an application programming interface that you can use to control robots. So we'll see how I would break it down for you into something very, very relatable that you can always look at and see, okay, this is how PyBullet works. And then we move on from there to programming real simulated robots using the PyBullet API. So when we examine all those small things about PyBullet, and we try to bring everything together to actually create a robot. So the robot we're going to be making here, I think I'm getting a feedback or something. Someone should try and make their mic. All right. Okay, so the robot we're going to be creating here is a kind of robot that is going to be, trying to look for another robot. So for this robot to look for another robot, it means that it needs to understand something called orientation. So we need to understand orientation, and we need to understand positioning when it comes to robotics. So we'll talk about that later. And then you see how you can program a robot that is going to find another robot and then move to where that robot is. Okay, so the second part of this webinar is where I'm going to make a demonstration. So in this demonstration, we have a robot from Husarian called ROS2. So this ROS2, I'm going to make it in such a way, this will be in ROS2, unlike the other one, which is ROS1. So in ROS2, we're going to make this robot go to a specific location. So we call it go to go. So we have the LiDAR. Using the LiDAR, we use the information on the LiDAR to navigate the robot to a particular position. Yeah, and that's very, very cool. Okay, so now let's move back to the beginning. So what is PyBullet? Why do you need PyBullet? Now, I think I really need to clear this part. The thing is that ROS2, to use ROS2, you need a lot of things. You need to mostly have a kind of Ubuntu computer. ROS2 is available on Windows, but people prefer Linux. And then ROS2 has a lot of packages that makes it very, very complex. So it's not that you can just use ROS2 right away. So if you want to simulate a robot in ROS2, there are so many things you need to put in place before you can have that robot simulation. And that's where PyBullet comes in. So PyBullet is like, hey guy, you don't need to stress yourself before you have a simulated robot. Like you want to do something very nice, something to move around, you don't need to stress yourself. If you can just get your robot model and you have Python on your computer, you're good to go just with a PyBullet API. So PyBullet is, the Py stands for Python, and the bullet is actually a physics engine. So the physics engine has a C++ a C++ version, and then they decide to make the Python version of the Bullet engine. So the Py and the Bullet gives us the PyBullet. So we have Python, and then we have the Bullet physics engine. So again, now back to the URDF. We're going to be discussing using the URDF, and I will send you this while the webinar is going on. So I will send the link to you right now. The link is actually a GitHub link that we're going to be using. It's from Reflect Robotics. Where is this link? I think my screen, I can't click anymore. Can I just move this guy? Okay.
Okay.
All right. Yeah, so this is the link here. I'm gonna put it in the chat section now. Yeah. It's always not easy figuring out things.
do you want me? Don't worry, I got it.
Okay.
I'll put up the link.
Okay, the link is on the chat section now. You
Okay.
can get it and clone the repository. So if you don't know how to clone the repository, we're going to do it right away. To clone the repository, if you're using a Linux computer, just type Control-C, or you open the terminal. Yeah, okay, you type Control-C to open the terminal. And when the terminal is open, you can just, do CD. So when you do CD, then you can create, okay, this is how we're going to do it. Let's first create a folder. So to create a folder, just type mkdir for folder, and then you just name your folder, whatever name you want to give it. I'm going to call it webinar 1 or something. Okay, and then I'll create access. So I can then go to webinar 1 and type cd webinar 1. Okay, so when I type enter, it takes me into webinar 1. Again, remember you type mkdir and the name of the folder, we call it directory you want to create, and then cd stands for change directory. So we want to change directory into webinar 1. So we go to webinar 1. Now that we are inside webinar 1, then we can clone our repository. To clone the repository, just make sure you go to Reflect Robotics GitHub page, and then you click on, okay, the link I sent to you. Yeah, the link I sent to you. So you just type git, and then you type clone. So you have to be sure you have Git on your system. Type git and clone. After that, you paste the link I sent to you. So when you paste that link, it's going to download the files. Okay, so you can see now I've downloaded the files and I have them here. So when I do ls, which stands for list, it's going to show me the folder. So I have the folder here called webinar 1, and inside webinar 1, I have a bunch of stuff. So the first thing I have here is Husky directory, and the next thing is the robot2 URDF. So you need these two files to be able to proceed in this webinar. So feel free to go through this mkdir to create a webinar, and go into your webinar, git clone, bring the webinar inside your computer, and then when it's inside your computer, then we're going to use it later. So let's go back to the webinar now. All right, so we are here understanding robot models. So URDF again stands for Unified Robot Description Format. And we're going to use this URDF to create our robot models. Without a robot model, there is actually nothing to simulate in PyBullet. Okay, so now we are here at the PyBullet installation. So to install PyBullet, I think we sent something to everyone. So to install PyBullet, let's do cd and be sure that we are at the home directory. And I want to be sure we are all following very well. So if you have cloned your GitHub repo file, if you are still having difficulty, okay, am I too fast?
Yeah,
so
I think someone wants you to slow down because
Okay.
I think they're
Well,
trying to.
my apologies. The robot is just trying to come out of my mouth, and I couldn't resist it. All right. So again, let's do it one after the other. If you are on a Windows computer, just go inside a folder, or you open your command prompt. If you're on a Windows computer, open the command prompt. When you get to the command prompt, then just type this git clone and every other thing like that inside the command prompt. So you should have these two folders downloaded into your computer. Okay, I think I can move on now. So,
yes, we have like a couple of people who are using Windows, but okay, you want us to paste the code. What I'm going to do is, for those who are not able to use
okay, we have
Gates,
people using Windows.
yeah, for those who are not able to use Gates, I would put the project on a folder, maybe on a Google Drive folder, and then share the link.
Okay, that's fine.
Yeah, so you can go on.
All right, thank you. All right, so now we are at the home directory. What we want to do, PyBullet. PyBullet installation is very, very simple. You just type sudo. Sudo means that you're giving the super user privilege, and then you type pip3. Pip3 is like what we're going to use to get the PyBullet, and then you type install. Install means that we want to install something, followed by what we want to install. And what we want to install is PyBullet. Okay, so when you type for you, so I have it already. Let me try it and see what's going to happen. Okay, so when you type that and you press enter, sudo is going to ask for a password. So I'm just going to put my password now. Press enter. So it's trying to get it. Yeah, I have PyBullet already, so I don't need to get PyBullet. It says requirement already satisfied, and it's telling me where my PyBullet was installed. Okay, so I'm just gonna give you like a couple of minutes to do that. Again, to install, let me just copy for those who are having issues seeing this. Okay, so the link is at the chat section. You have sudo pip3 install PyBullet. Okay. Now that we have PyBullet installed, we can actually start using PyBullet right away. So before we start using PyBullet, I just want to, while some of you are still trying to install, I want to bring to your remembrance the Reflect Robotics course that is, on right now. We have a course called ROS2 for beginners, and I want you to take the time to look at it. It's very, very interesting. This course, you get, how to use Robot Operating System 2. So Robot Operating System has the 1 version, which is, outdated now, like all going out of phase. Now we have the ROS2, and some people find it difficult to catch up with ROS2. We have a course already that is already on, so you can check our website. And if you need to get this course, you can just contact us. So it's called ROS2 for beginners. We're going to teach you how to use the Robot Operating System 2 to program robots in Python and also in C++. Also, in this course, you'll be learning how to use object-oriented programming. All right, so I hope you've been able to get the stuff ready. Now, let's continue. So we're going to create some stuff right now. And the first thing we're going to do is to create a folder, because we want to work, we want to do something. So we need to create a folder for our work. So I'm just going to call this folder Robot Workspace. So to create a folder, I'm going to say cd or mkdir, which is make directory. And then I should make this thing bigger. Yeah, I want you to be able to see. Okay, so I have mkdir here, and then after typing the mkdir, the directory I want to create. I'm just going to call my directory robot workspace. Yeah, that's all. And type cd robot workspace. So I am inside the directory right now. I hope I'm being heard. Hello, Yeti. Can you hear me?
Yes.
All right, thank you. So I'm inside the robot workspace right now, and we want to start creating our project. So the project we want to create, let's just call it robots.py. You can just give your project any name. I'll just call it, you use touch to create files. Now, if you are on Windows and you are surprised, like, what's all this command? Please just use your mouse and type open a new file. And then when you type open a new file, just give your file a name. And after giving your file a name, you can then type the extension that you want your file to be. In our own case, because we're writing a Python code, so the extension is going to be .py. So I'm just going to call it robots.py. All right, so we've created a file now called robots.py. So I can now open this file with VS Code. So to open the file with VS Code, I'm just going to type code. Remember, we said to you guys that you should have a text editor like VS Code, and you should also have the Python 3 installed. So I'm going to type code, and then dot means that I want to open the current directory. So it's going to open VS Code for me. And right now, there is nothing inside robot.py. Okay. So we want to create some things inside robot.py. This is where we start the PyBullet code. The first thing in PyBullet is to import your file, the library. So the first thing you want to import is PyBullet. Sorry, I think I'm getting. So the first thing you want to import is PyBullet. And then you'll say import PyBullet as P. Okay, so after that, you want to make sure that you have. Am I too fast?
They said yes. Someone else said no. But please try to be on the average,
Okay.
Yeah. Please slow down.
I'm gonna move slowly now. But yes, I want to be sure. Let me check the section. I want to be
many
sure.
People are still behind.
Following. Okay.
If you're following, please put the number 1 in the chat. If you're not following, put 0.
Just type 1.
If you're not following, put 0. Okay. 0. 2 zeros. Thank you.
Okay. Okay, Hamza is following, Jimo is following. Okay, Adeyemi, Christopher is following. Very nice. Very nice. Who else is following? Who is not following?
Maybe we can slow down a bit because some people just got the code. Okay. Yes. So we can just slow down a bit.
Okay.
Some people just got the access to the Google Drive for those who were not able to use Git.
Okay.
Yeah. Okay. So we have quite a number of zeros. So let's just slow down a bit.
All right. Okay, so while we're waiting for others to catch up, let's quickly, reiterate on something. So again, the pipe is going to be using to control a robot. And the robots we want to control, we have the models of the robots in the GitHub link that we just cloned, or the GitHub repo that we just cloned. Clone means that we just downloaded it into our computer. Okay, so we have the robot models already. And in these robot models, I'm going to be explaining the URDF very soon, which stands for Unified Report Description Format. Now, before we do the URDF, I want you to know that there are different ways to model a robot, or there are different file extensions. URDF is just one of them. We have the SDF, which I think stands for the Semantic Description Format. We have the Zacro, the .zacro. We have the I think those are the, like, yeah, we even have .world. It all depends on like the kind of model that you want. And these extensions, they all have specific information that they carry. They all have like, a little bit of differences, but basically they are just a way to describe a robot model, not just a robot, but any 3D objects, any 3D objects. So this URDF, we're going to import it now, but before we import it, let's go back to our VS Code. So the next thing we want to do now is import PyBullet underscore data. So you need to import these two things before you can work with PyBullet. Now the PyBullet underscore data is just a way to get some pre-installed files in your PyBullet, so which we're going to be using now. All right, so in PyBullet, I'm gonna make this big as well. Looks like that's too much. Well, trying to make it small. Okay, I think that's fine. So in PyBullet, we have some set of stuff. The first thing you want to do, remember we imported PyBullet as P, then you want to do P, like P is like the access point to everything you want to do. P is like the access point to the API. So it's like we have a house called PyBullet, and we are saying import PyBullet as P. P is like a representation of PyBullet. So anytime we need to use the APIs in PyBullet, we go through P. So P is the door. We pass through P to be able to get to PyBullet. Okay, so we say P dot connect. Now this connect is the one that connects to the physics engine. Remember, we're trying to simulate, models. So this connects you to the physics engine, and then you say P dot GUI. So this way, we are connecting to the physics engine. So we are connecting the GUI system to the physics engine. From there, we can, do other things, which is the next thing is we want to set the additional path. I'm gonna explain what this is doing. So set additional path. Now set, or let me say set additional search path. Now, what set additional search path does is that there are some things we want to use, and those things came with Python. So we want to be able to fetch the path where we have those things. In other words, you can see the path as a directory or the path as a folder. So we want to get the location of that folder so that we can use it in our simulation. So we're going to say p.set additional search path, and then we put in some parameters inside. The first is the PyBullet data dot get data path. Okay, so the PyBullet data dot get data path. All right. Oh, sorry, we need to close this guy. So after putting that, we want to create a plane. But before creating a plane, let's just see, is our simulation engine even working at all? So I'm just going to say while true, then we want to run the simulation engine. So to run the simulation engine, remember P is like the entry point. So we say P step simulation, and then we pass in this. Okay. Time, let's sleep. Now we have not imported time yet, so it's not going to work. So we need to bring in time. So I'm just going to say import time. Okay, and we have it here. So let's run our simulation and see how PyBullet looks like. So to run the simulation, I don't know where my terminal went to. Where is my terminal? Anyways, so to run the simulation, I'll just go to the terminal. And then remember, we have the robots.py inside. So I'm going to run the code now. To run the code, I'll type Python 3. And then we have the name of the file we want to run. It's robot.py. Okay, so we can see it quickly, it showed something and then because we don't have some things yet. Okay. Oh, I get it. We didn't put in the time. So I'm just going to say 1./240. Okay, I'm going to run the code again. Okay, now it stays. So what happened the other time is that I didn't pass any parameter inside the, any argument inside the parentheses. Now this is how PyBullet looks like. Very simple, very basic. You can use your mouse to hover around. You can, you can tilt, you can zoom, you can pan. You can go any direction. You can use your mouse if you have external mouse. If you don't have external mouse and you want to, rotate the environment, you just press the control on your keyboard, and then you use the mouse on your laptop. So you can always go this way, go that way. So the color coding here, we have the blue, we have the green, and we have the red. So the blue stands for your z-axis. So we have the z-axis. If you have an object, objects are usually represented by their position and orientation. So it means that you can move along the z-axis, you can move along the y-axis, and you can move along the x-axis. Also, for the orientation, we have the roll, the pitch, and yaw, which we are going to get to later when we start, writing code to control the robot. All right, so these are the three axes. The blue is the z. I think the green is the x, while the red is the y-axis.
All right. There is a question.
Okay.
Someone asked why sleep is one. I think it's check the chat so I don't.
Okay.
Yeah. Is the AG conventional, and why sleep is?
No. It's okay. So the timing stuff is it's a module in Python that you can use to control how a particular thing should run. So it's something we use in ROS as well. And the timing function here, the sleep function, actually takes in a double parameter. So, and the double parameter we pass here is just this 1/240. Now, it doesn't have to be 1/240. This is just like a time. I think it's a frequency. I can't remember right now. But I think it's a frequency or seconds. Yeah, but it doesn't have to be 1/240. Is that okay?
Okay. Yes, all right. Please go on.
All right, thank you. So again, we have our simulation like this. So nothing inside. We have some stuff by the side, the Explorer, which most times you don't really need because they don't really contain so much. But anyways, in Python, you can attach camera to your robot. So we have the synthetic RGB, the camera, the depth camera, and so many other things like that. So Python is, sorry, I said Python, PyBullet is actually used in not just in the industry for simulation, but people who use PyBullet most are people in the academia. So because they want to actually, simulation is very important to people in academia. It's not all the time you just want to like control a real robots directly. So they quickly use PyBullet to test and see how things behave. So it can really go complex. It's as complex as you want to go, but it's right now it's a very basic thing. So I'm gonna close it now, and then we start putting things inside. All right, so let's go back to our code. So we have this code here, and if you notice the other time, you will see that it's like there is no flaw when we open the PyBullet. There was no flaw. So this time, we want to put a flaw, or we want to add a flaw in PyBullet. To do that, you can just add the flaw and store the value, in wherever you want to store it. I'm just putting it inside plain because the name of the flaw is plain. So I'm going to say p.load URDF. Remember, URDFs are the ones that describe the physical properties of your robots. So we want to load the physical property of the ground for the robot we're trying to create. Because if you do not create the ground, the robot is just going to fall off because it's going to be acting on gravity, or gravity is going to be acting on it. So it's going to fall off. So we need a ground such that if the robot even tries to fall, it's going to land on something. Okay, so I'm just going to do URDF, and then I call it plain. Now you might be wondering, where is plain coming from? We have actually not attached anything to this our environment, but where's plain from? So plain is coming from PyBullet data.getDataPath. So when you trace this guy, you will realize that it has some bunch of information, and part of the information in this path is the plain.URDF. So we are actually going there to fetch the plain.URDF. So I'm going to launch the simulation again. I don't know why my timeline is not showing here, but let me just use this. Okay, now you can see we have a ground, and this ground has been tiled like blue, white, blue, white, blue, white tiles. So now we can have a place for the robot to stay. It's not good for a robot to be lonely or to be alone. It's not good for a robot to be alone. All right, so it's going to stay on this plane, and then we're going to put something there. So now let us go back to the URDF thing. We really need to explain URDF. So to go back to the URDF, I'm just going to open so you can go to where you cloned or you copied or pasted the GitHub link I sent to you, where you put the files. So mine was webinar 1, I think. And then inside webinar 1, I have these two guys. Okay, so I'm going to copy these files, both of them. I'm going to copy them and then put it inside the one where we have our code right now. So I'm going to go back to home. I think I created robots workspace. Where is it? This is it. So I created robot workspace, and I'm going to put them here. So what we got from the GitHub is now in our directory here called robot workspace. Okay, so I have Husky and I have robots2. So let's see what's inside Husky. Okay, so Husky has husky.urdf. All right, and it also has meshes. Okay, so Husky is actually a robot built by ClearPath Robotics. ClearPath Robotics is a robotics company in Canada. So they are the ones in charge of, Husky and some other robots like that. So we have Husky and we have meshes. Meshes are files that describe the shape of a robot, okay? So they describe the visual representation of a robot. So we have this mesh files in STL formats. This is the kind of formats that you can take to a 3D printer, and it's going to slice it for you and then print the parts. Okay, so these are meshes. So it means that URDF files, they can also rely on other files, and some of the files they can rely on is STL files. They can also rely on .dae files. Okay, so I'm going to go back now and let's go to our code. So in our code right now, we have the Husky, and then I want to open the URDF. Now see what's inside the URDF. a whole bunch of information. Remember I said Husky was made by Clearpath Robotics. This is it here. Okay, so URDF files are defined in a certain way. They are actually markup languages. For some of you who are familiar with programming HTML, HTML5, like web development, you might be familiar. Or for some of you who are familiar with files like YAML files and something like that. So this is a markup language, and this markup language can actually describe how a robot looks like. So let us see. To create a URDF file, you start with this tag. So there's a whole bunch of stuff here. So that's why I don't want to, we can't start typing all these things. It's very long. Okay. So to create a URDF file, you have to start with this tag, the XML version, and then you have to start with the robot. So when you start with the robots tag, you also end with the robot tag. You can see here, it was ended with a robot tag. So inside this tag, the robot, we have a whole bunch of information about how our robot looks like. For instance, for the people who created this file, firstly, they created like a color materials. So, colors are in RGB. So we have the R, the G, the B, and the alpha, which is 1.0. Okay, so they did this such that they can always call the name of this color anytime they want it. For instance, I guess this black color is going to be used for the wheels, to tell the URDF file that we want to create wheels, and the wheels or the tires, they are actually black colors. Okay, so that's why they created all these color tags. So from there, they started creating links. Now I need to explain something about link. Maybe I'll just take one of them. So links are what connects your robots together. For instance, let's say you have a robot or a car. The car has a chassis. So that chassis, we usually call it the base link. Why is it the base link? It's the base link because every other thing connects to that chassis. Your wheel is connected to the chassis. Even your dashboard have a way of getting this connection. Your steering is connected to the chassis. Every other part of the car, they are almost like they are connected to the chassis of the car. So that's why we call them base link. It's like the base of the car. So it's a similar thing in robots. So we call them links. So when you have a chassis, it's a link. When you have a wheel or a tire is also a link. So all these links, they connect together to form a single robot. Now that's for robot cars. If you are dealing with drones, you also have links. We have, the right wing, the left, we have the rotors and every other thing. So they are also links. When you're dealing with robot arm, so you have a robot that can pick something and put it somewhere. And each of the arm has different joints. I mean, each of the links, they are connected by joints. So we have a link, you can refer this as maybe my elbow or my arm, and then you refer this to something else. So they are like, this is link 1, this is link 1, this is link 2, and link 2 is connected to my hand or my fingers, which is the wrist. Okay, so that's how link works. So link is just about that particular object that connects to another object of the robot. They are called links. Okay, so links are connected by joints. So we'll get to joints later. So I'm just saying all this because you need to understand the URDF. If you don't understand URDF, you might not really be able to interact with the robot model. Okay, so your links need to have a visual. And then the visual, this is the starting tag and the closing tag. The visual has a lot of things inside. It has the origin. Okay, remember, we are just talking about a particular link right now. So the link has its own origin. All these things are, very, very important because they describe where the robot is at the moment. And they even describe how the robot looks like. Okay, so we have the origin, where we have the RPY, that stands for the roll, pitch, and yaw. The roll, pitch, and yaw, they are called Euler angles. And these Euler angles, they describe the orientation of the robot. For instance, look at the phone here. I have a phone here. So this phone is like this. It's at the position, let's say 0, 0, let's say 3, since the z-axis is up. Okay, so it's at 0, 0, 3. Now that is just telling me about where this phone is. It's actually not telling me the orientation of the robot. It's just telling me where the robot is or the phone is. So if I need the orientation, query the RPY, which is the roll, pitch, and yaw. So we have the yaw this way that describe how the robot is this way, and then we have, we have the pitch, and then we have the roll. Okay, so that's the RPY. While the XYZ is the one that describes the position. Where is the robot? XYZ will tell you. Where is the robot facing? RPY. So geometry is telling us that this particular link, which is
Hi,
called
Lekon, can you hear me?
is connected to a mesh file called meshes/baselink.stl, which is what I showed you the other time. So not to waste time, we can also see that this link is colored, it's having a color and complete visual.
Hi, Lekon, can you hear me?
Yeah, I can.
We lost you for like 30 seconds. If you can repeat yourself.
Did I proceed?
Yes, but we lost you for like 30 seconds.
Hello?
Can you hear me? Okay, I think we went off. Please give me one moment here. Okay, you're...
Hello?
Yeah, you're back now.
I think I was taken out or something.
Yeah.
All right. So where did I stop, guys? Hello?
Can you share back your screen?
Okay, yeah, I will. I'm asking, where did I stop, guys? Hello?
Oh, sorry,
Hello?
I was
Can you
muted.
hear me, please?
Yeah, so you stopped at XYZ. You've explained the row picture already.
Okay. Okay.
We're describing the position. Yeah.
All right. Thank you so much. So again, I would just like summarize what I said now, that this is the position of this phone. I hope we can all see the phone. This is the position. This phone right now is Y, Z. Okay. So the X is for the X axis of the phone. The Y. So I can say the robot is at 005. So 005 means that it's at a position X of 0, position Y of 0. And because it's elevated, you can see it's elevated, I can say that the Z is at position or 10 centimeters. Okay, so that's the XY. It doesn't tell you how the phone is. Is it like this? Because all 10, but we don't know what's the orientation. And that's what the RPY tells you. The RPY is the roll pitch here, and they are called Euler angles. We also have quaternion angles, which we are going to deal with later. All right, I'm going to move on now. So again, the visual tells you how you can see how the robot looks like. But the visual has a limitation. The visual only tells you that, okay, this robot looks like this, but it doesn't tell you whether you can interact with this body. Now, when I say interact, I mean, if I get close to this object, is my hand going to pass through? That's what I mean by interact. Is it an object where if I should try to put my hand inside, it will pass through it? So when you define the collision property will tell you, okay, this object is like a solid object that you can't pass through. That's what the collision is going to do. So it's going to take like the same dimension and then tell you, okay, you can't pass through this object. That's what the collision is going to do. Then we move to the inertial. The inertial property of a URDF, I'm going to stop the URDF very soon, but the inertial property of a URDF tells you, the mass of this object, the inertia of this object. I don't want to make things, complicated for you guys, but you can always check out later what inertia is. The inertia values, for some of you who might be familiar with some mechanical engineering terminologies, the inertia values tells you the IXX, the IXY. These are properties that defines how an object looks like, okay? All right, so that is that. Now I'm gonna move, like all these things are basically almost the same. So I'm gonna move to this part. This part talks about transmission. So transmission, it's another tag in URDF. It tells you how the links are connected, what kind of joints are you going to have with this link. So we're saying that we have a motor called the left wheel motor, and we want to connect it with something else. So we're trying to tell you the kind of transmission mechanism is called the simple transmission. And then we tell you what joint is connected to that actuator. Anyways, enough of this talk. Let's go to the programming aspect. So because the programming side, I will still show you all these things. So let's move to robot.py right now. And then we've been talking about this particular model. How can we use it? So I'm going to bring in the robot model right now. So again, the robot model, I'm going to call it robots. Please, Yeti, if you can hear me, I just want a signal from you. I want to make sure I'm being heard.
Yes,
okay?
yes.
So we have a robot model. And then this robot model, sorry, please. All right. So this robot model, we want to load it. So again, we do load URDF. Now let's go back here. You can see we have robots underscore workspace, and our robot underscore workspace. Okay, so I'm just gonna say we have this guy under my own is called. I want to in fact mention all the paths. So my own is called home. I'm under Olamileko. That's the name of my computer. But if you don't want to go this way, you can just start from the robot workspace. So home, Olamileko, that's the name of my computer. And then I'm going to type in my robots underscore workspace. Don't forget where I'm actually going to is this husky.urdf. So I'm trying to bring the location where that husky.urdf is. So the next thing is husky, which is also a folder. And then after husky, you have the husky.urdf. Okay, so with this now, I have my robot. Okay, and I'm loading my robot inside this thing called robots. Okay, let's launch our simulation environment again and see what is going to happen. Okay, I'm just going to go to terminal and then we launch again. Okay, so we are having problems. And then what is the problem? It's saying, where bumper link, I'll share a simulation frame. Okay, we have a problem and no initial data for link. Okay. I think some information about the robot model is missing, but that's no problem. Gotta fix that. Okay, it's failing because there are some things about this guy that is not known. Okay, there's some things about this guy that is not known, but that's not going to be a problem. Let's just move on with our code. So now that we have the robot model, the next thing we want to do is to set the gravity for this robot model. So to set the gravity, set gravity, set gravity. And the way the gravity works is you pass in the 0, 0, while the last one is the gravity value, which is usually -10. So that's the recommended thing from the PyBullet API. So you put the gravity there, and then we're going to run our robot again. Actually, it's bringing that error. No initial data for link using +1. This one. Okay. Let me cancel that right now. I need to, let me check and confirm the link again. You can try to run the code. Let me know, guys, if it's working from your side. There's something I'm missing here. PyBullet. We have the ROS key, and I think it's the same thing. Okay. So I'm going to try it again. Oh, I'm having it one. Okay, we're going to do something. Let's leave this guy and use the second model. The one is coming from the initial data. We're going to use the second robot model. So to use the second robot model, remember we have both of them inside the workspace. So we have them inside the workspace. So I'm just going to use the robot2.urdf. So to use the robot2.urdf, come back here, and then you put robot2.urdf. So let's run this and see what's going to happen. Actually, this is the robot we're going to use for our simulation today. Okay. Sorry, I just realized it was actually working rather. So let's change it again. It was actually working. It's my laptop that has so many tabs. So I've changed it again now, and then we have it here. This is it, yeah. My laptop had so many tabs, so I didn't know that it was actually showing. So this is the robot, the Husky robot. There are so many things about this Husky robot that we are going to get in this tutorial. Okay, so I'm going to close it right now. Again, this is how you learn, you spawn a robot. You use the load URDF and then you set the gravity. Now let's comment out the gravity part and see how our code is going to work. Okay, can you see that without the gravity, the robot is floating? The robot is floating. So when we add that gravity, it makes the robot stable and tell us that this is actually an environment where gravity acts. So I think it kind of looks like you can use PyBullet in a space environment where you can set the gravity. Okay, so we're going to put it back. I'm just going to cancel it right now. I want to be sure I'm audible. Okay, so let's run it again. All right, so we have it here. Now, again, we want to get some things about our robot. I'm just going to take this guy. Sorry, just give me a second. There's some things about this thing we want to get now. The first thing is we want to see what is the joint in this robot. So to get the joint, I'm going to put out and say, just print. So when I say print, I now want to put what I want this thing to print. So what I want it to print is the number of joints that this robot has. So to get the number of joints that the robot has, I'm going to use P of joints. Okay, so then the question is, which robots do you want to get its number of joints? So I'm going to put it here that I want to get the number of joints of this particular robot. Again, Yeti, I want to be sure I might be heard. So we do p.get number of joints, and I want to put the robots that I want to get its number of joints. So I run this code, and you see that it should print the number of joints to me. Okay. So can we see here that the number of joints is 10? Yeti, please, am I being heard? I want to be sure my network is not.
Yes,
okay.
yes.
All right, all right. So the number of joints is 10. This robot has 10 joints. Remember, I said that joints is what connects links together. So this robot has 10 joints. Now let us see, or let us get information about the joints. So remember, it has 10 joints. So we're going to get information about those 10 joints. I'm going to cancel it now. This is where things are actually getting interesting. So I want to get information about the joints. For I can just call it I in range. For I in range, so what is the range? The range is the number of joints. Now it's like I'm hard coding it. I want the code itself to be able to get the joints we are referring to. So I'm just going to say p.get number of joints. P.get number of, capital N. P.get number of joints, and it's the robot. Remember, it's actually 10. So for every joint in the robot, we'll get information about that joint. Do you understand? So for every joint in the robot, we want to get information about that joint. So I'm going to say p.get joint info. Okay, p.get joint info, and we're going to query it. It takes two arguments. The first is the robot model, and the next is the particular index of the joint. Okay, so the robot model and the index of the joint. So for every joint, we want to get information about that joint. So I'm going to run this now. Remember, we have 10 joints. Okay, so I think I should make my VS Code do something. All right, so you can see a whole bunch of information here. The first joint is called the chassis joint. Now let us go to the URDF to confirm. Is it true that the first joint is the chassis joint? We are going to confirm now. Okay, all right, can we see it here? The chassis joints, this is it here. Okay, So the next joint is called the IMU joint. So this has index 0, index 1, the IMU joint. The IMU joint is the next joint. Let's see, is it here? Wow, this is it, the IMU joint. So what about the next one? The front wheel. Okay, let's check. Is the front wheel inside? Wheel joints. Can we all see that the API is able to read what is inside the URDF and give us information about several things inside the URDF. So when you use the get joint info, it gives you so many information about the joint. It gives you the index of the joint, the name of the joint, the position and orientation of the joint, and so many other things like that. Okay, so I'm going to cancel this code now. So to show you that that is how you can get the joint info. All right. I need to bring my terminal up. Yeah, I have my terminal here now. All right, so that is the information about the joints. Hello. Okay, so the next thing we want to do.
Yeah, we can hear you.
All right, great.
Don't worry, if you can't hear you, I will mute and tell you.
All right. I always feel like I'm not talking to the head.
I know, but I was thinking, do you think we should have like a 10-minute break now?
Okay,
so that people can absorb everything.
Yeah, you need to digest.
If you want a break, can you like put a number 5 in the chat? I'm sure a lot of people are serious. Yeah, like people want a break.
Yeah.
Only one person wants a break. Okay, maybe we should go on. If it's just one person that wants a break. If you want a break, can you put the number 5 in the chat?
Okay, it's just all right. It's getting technical.
Okay, we'll go on a 10-minute break.
All right.
Yeah, I think that's better.
All right. So we are going to be stopping in some minutes time. We really need to, in like 20 minutes or something. So we really need to move fast. So I want you to catch up with what we're doing. So I'm going to share my screen now. All right, so we have seen how to get information about the joints. Also, we have seen how to set the gravity and how to load the URDF. So the next thing we want to do now is, let's see, remember I said a robot has a position and orientation. So let us see, can we guess the position and orientation of this particular robot? Okay, we shall see very soon. So I'm going to call this position, and then I will have orientation as well. Okay, so position and orientation, what do I want to put inside? What I want to put inside is P dot get base. Now, these APIs, they are just like functions that you can use inside your Python. So it's a p.get base, and then inside the get base, we have the position and orientation. Yeah, I think position and orientation. Okay, so the position and orientation, we then need to tell it position and orientation of which robot. So I'm going to put this particular robot, which we created at line 8. We're going to put it inside. So this way we can get the position and orientation of the robot. And then I'm just going to print out the position. Okay, now the position, again, remember it's 2 things inside, the X, Y, and Z. And then the orientation. In robotics, we describe things, the orientation of objects, either using Euler angles, which are the row, pitch, and yaw, or using quaternion angles. So quaternion angles give a better description of the orientation of a robot. There's what we call orientation locking or something like that, where Euler angle is not sufficient to describe orientation of some particular object. So for the PyBullet API, the orientation is in quaternion. So you can always convert from quaternion to Euler angles, which we're going to do later. So I'm going to print the position, and then we print the orientation. Basically, we are looking at how we can use this PyBullet thing. Okay, I'm going to run my code now. I think I have it here. So Python 3, what's the name again? Okay, over to Py. Okay, so down here, I can take your eyes away from the GUI. Down here on the terminal, you can see we have the position. The position is 0, 0, 0. This is the position, and the orientation, the X, the Y, the Q, and the W. So that's for the quaternion. So it gives you three, it's a list, and inside this list, you have three things inside. In the other list, you have 4 things inside. Okay, so that's how you can get a position and rotation of the robot. So what we are going to do now is that instead of going through step by step, we are now going to start creating our own simulation. Again, what we want to do is this: we want to have an environment in such a way that we have 2 robots in the environment. When we have 2 robots in the environment, we want one of the robots to look for the other robot. So when it sees the other robot, then it should go and meet the other robot. Okay, so I'm going to quickly copy this and paste it here. So we have the robot. I can just call it robot 2, and then it's also in the same directory. So we have both robots right now. Then what we want to do is we don't need all this get range and stuff anymore. So even the position and orientation, we're just going to take it away. We don't need them here right away. So now let's go back into our loop, the while true, because we want this code to continue running and running until the task is completed. Okay, so we're going to get the position and orientation of the robots. So I'm just going to do position of, I'm going to call this the first robot. Sorry for this very bad naming convention, but let me just use pose. The robot, the first robot, robot 1. So let me call this robot 1. Okay, so the first robot, robot 1, and then the orientation of, okay, I'm just calling orient of robots 1 as well. So what we want to put inside is still the p.get base position and orientation. Okay, so we want to get the position and orientation of robot 1. Okay, when we are done with that, we want to get the position and orientation of robot 2 as well. So I'm just going to call this robot 2, and then we call this robot 2, robot 2. So we need that information. We need it. Okay, so after getting the position and orientation of our robot, what do we need it for? Okay, we need it to calculate where the robot is facing. Okay, so to be able to calculate where the robot is facing, we need to convert from Euler angle to quaternion. Okay, so I'm going to create an angle called theta. And what theta does is to get the angle P dot get Euler from quaternion. So you want to get Euler from quaternion. Okay, so you want to get Euler from quaternion, and what's of our robot 1, and then this orientation of robot 1. Remember, it returns 4 things. The, what do we call it again? Oh, sorry, we are converting it to Euler right now. Okay, so it's in quaternion X, Y, Z, W, X, Y, and QW. So we want to convert it to Euler, which is RPY, row pitch here. So it's a list. It's going to return a list back to you. And inside this list, we have three things, the RPY. We only need the Y because our robots can only rotate like about the Z axis. Sorry, I mean, we need the Y. The Y stands for yaw. So our robot can only rotate about the Z axis. That's why we need the Y. Okay, so to get it, remember the index starts from 0 for R, the row, 1 for pitch, the 1 for pitch, and then 2 for yaw. So we just use 2 like this. So it means that we are getting the the third position, which is the second index. And then we want to put it inside theta. So we know the angle our robot is facing right now. Okay, now that we know the angle our robot is facing, we need to know the angle of the other robots as well. We need to know where is that other robot also facing. So to do that, we get the X position. So I'm just gonna say this theta is for robot 2. Sorry, for robot 1. And then we create another one, which is, let's get the position of robot 1. Remember, inside this position of robot 2, rather, inside the position of robot 2, we have three things, the X, Y, and Z. So this X, Y, and Z, we are interested in just the X and Y. So I'm gonna call it X2, X2. X2 stands for the X position of robot 2. And then I'm just gonna call that position of robot 2. And then we are getting the first element, which is 0. Okay, we do that for the Y position of robot 2. We get the Y, which is 1. Okay, remember we have three things inside, 0, 1, 2, making 3. All right, now that we have those three things inside, we need to perform a mathematical formula which says that if you want to get the angle at which an object is facing, you want to get the angle at which an object is facing, you need to take the arctan, the tan 2 theta, okay? So the tan 2 theta here, or arctan 2 theta rather, so it's going to use the math library from Python, so I'm just going to import it right here. So I'm going to do import the math library, okay? So from there, we can then say, what do we want to get again? We want to get math dot arctan 2, and then we pass in the X over Y. So if you want to get the where something is facing, you take the X position of that object, and then you divide it by the Y position. So the X and Y divided by Y, you then find the arctan of that object, okay, of that number. So we're going to pass in the X2, comma X, comma Y2 rather, comma Y2. So with this, you can get where it's facing, okay? So we can then store it in angle 2. Now, the angle 2 is just for anything that is happening to is for the second robot, okay? So now that we know that, then we can try to subtract. So if the absolute value, now we're getting into some very small mathematics here. So if the absolute value of this angle which we just created minus this, that robot. Sorry, I think I should clear something here because it's might be confusing to some of you guys. So what I'm saying is that I want to take the angle at which the second robot that is not going to move. That one is just going to stay in a particular position. That's the one we are looking for. So we want to subtract that angle from the angle of this one that is moving around. So we want to subtract from the angle of the one that is moving around. So when whether they are actually in line, like they are in the same, they are facing the same place. So if not, if it's greater than 0.2, we just pick that number. So if it's greater than 0.2, then we want to do something. What we want to do is we want to set the linear velocity. Let me just call it linear velocity to let's just say 0. Yeah. So basically what we're saying is that if they are already in line, if there's already if it's greater than 0.2, they are not in line. We want the robot to turn. So we want to give it an angular velocity. So which I'm going to put here, angular velocity. So we want the robot to turn in the direction of the second robot. So let's just say 7.0 or yeah, let's do 0.7. So we want it to turn in that direction. Else, you need to push the other. Sorry, what am I pressing? So we need to put the other thing here. Rather, we want to increase the linear velocity. So the linear velocity right now should be 0.7, while the angular velocity, okay, we are saying that this robot and the other robot, when they are in the same point of direction, then we don't want to turn, we just want to go straight. So that's the else part. But if they are not in the same direction, we want to keep turning until they are in the same direction so that we can now go to that direction. Okay? So that's that. So we come back here. Now, because this is inside this place, let's declare it outside. It's going to see it as a local scope, at a local scope. So let's declare it outside and initialize it to 0. So it's initialized to 0. Then we come outside. Then we say that the velocity of the right wheel, is equal. Now, this is a formula in differential drive robots, where you want to get the velocity of the right wheel and the velocity of the left wheel. So I won't really bother you much about the formula because we have limited time. So I'm just going to give you the formula. So it's 2 times the linear speed, minus the angular speed, and then multiplied by 0.3. So let's multiply by 0.3. Now this has to do with, omega, the angular speed. It also has to do with the distance between the wheels. It also has to do with the distance between the wheels of the robot. Okay, so I'm just going to do divided by 2 times 0.04. Okay, so I'm going to do Ctrl-C, Ctrl-V. Let's just be sure that we're getting our parentheses right. Okay. All right, so that's it. So we're going to calculate for the left wheel and the right wheel. So the formula says that if you are using VL, then it's going to be plus. If you are using V minus, VR, which is the velocity of the right wheel, it's going to be minus. So again, we want to declare, we want to set our VR and VL here. So the next thing now is we start putting in the velocity inside the robot to move the wheels. Okay, we build in our orientation, then we want to start moving the wheels. To move the wheel, we need to do something. So we're going to use P thoughts. Now, according to the API, there are different ways to control the robot. You can use what we call the velocity control. You can use the position control, and we can use the torque control. So you can control an object based on the position. You can control an object based on the velocity, and you can control an object based on the torque. Now, from the reference, they advise that if you want to control the torque, control an object with the torque, then you need to be very, very careful, because it means that you actually really know what you're doing, because torque will be really, really particular about some things. So in this case, we are using the velocity control. So to control the motors or the joints, the velocity of the joints, we just say P dot, then set joint motor. Set joint motor control 2. Yeah, that's it. So then you pass in some parameters. The first parameter you pass in is the ID of the object you're trying to control. In this case, we're trying to control the robot 1. So the ID is robot 1. It's a unique ID. It's inside. The next thing what I'm trying to control. Okay, I'm saying I want to control joint 1. Yeah, I think it's joint 1. So I want to control joint index. Joint index 1. Okay, so index 1 stands for one of the wheels. Then we move on. Which type of control do you want to use? So I'm going to say that the control mode I want to use is called velocity control. So I'm going to say velocity control. Remember, we have the position, velocity, and the torque. Okay. Then the last thing which has to put in inside this method. So we have the force. So the force, I'm going to declare it up here and just say the force, or let me call it maximum force. Maximum force is 30. And then I will call the force is maximum force. All right. So what I did here is for one of the wheels. I'm going to do the same thing for the second wheel. Okay, this is the second wheel. It's still same robot 1, but the joint index now has changed to 2. Okay, so we have the second wheel and it's going to move. Oh, there's something I missed out here. It's called the target velocity. I was wondering what is really going on. So it's called the target velocity. So after the control, then the next thing you want to say is the target velocity. In our own case, the target velocity is VR for the right wheel, while for the left wheel, the target velocity is VL. Target velocity. So this is moving or to keep turning. All right, I hope everything is set. Let's just try and see if we are good to go. Okay, so no, we are not good to go. Remember, this is the Husky model. What we need is this other model, robot2.urdf, which we actually launched at the beginning. .urdf, not the Husky. Why am I using the robot 2 and not the Husky? The Husky has 4 wheels. So for its kinematics representation, okay? So I'm just going to say we are still under robot workspace, and then so let's run this now and see if okay, we have an error which says force equals max force. So what is the problem?
It's a syntax error. Maybe you're missing a comma.
Oh, yeah, thank you. A comma. A comma. Yeah. Okay, so I'm going to run again. All right, we have it and it's quickly shuts down. So why are you shutting down? Something must be wrong. So we can always check why is it shutting down. Okay, set our gravity. Yeah. We get our position and orientation. Okay, we can check the error here. It says theta R1, PyBullet has no attribute get Euler from Cotanium. Okay, let's check. Where do we have that? Get Euler from, it has that. Euler from Cotanium. Okay, anyways, it's not a problem. We can always check the data sheets if we come across any issue like this. Get Euler from, just trying to see if I spell Cotanium very well. But anyways, I think I have the manual here. Okay. And then we're just going to search. You can always like query the manual or the API data sheets. Get oil or Tanya. Okay, so this is it. Now it's correct. So I don't know.
Or is it capital letter of F?
Oh, capital F.
Capital F.
Yeah, capital F. Oh, imagine. Thank you. All right, so I'm gonna launch again. Oh, that's terrible. Can you see it's terrible? Oh, I get it now. I get it. I get it. I get it. I get it. So this is the problem. We are trying to launch two robot models at the same location. So it's like you want to launch two things like a robot, you want to put it under another robot. No, 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 no. That's not what we want to achieve. What we want to achieve is that the other robot should be far away from this robot so that it can look for it and then go to where it is. So this is not what we want to achieve. So this second robot, I'm going to launch it far away. So this load URDF stuff, it does not only take this kind of string, like the path where the URDF is, it can also take where the URDF is, the position. So, and for me to put in the position, I'm just going to write something here and say pose is equal to, now remember, you can have, let me just put 3, 0. Remember, positions are X, Y, and Z. So I can then put it by the side here and say pose. So I'm just basically making a list, and then what is inside is 3, which is for X, 3, which is for Y, and 0, which is for Z, meaning that our robot is going to be on the ground plane, okay? So I'm gonna launch it now, and it should spawn the other robots at a different location. Okay, you can see now it's going to meet the other robot. Okay, now it keeps going. We didn't put a check for it to stop. Yeah, it keeps going. We need to put a check for it to stop. Oh, no. Okay, I'm gonna cancel that right now. So we need to tell this robot when to stop. And when it gets to that location, it should stop. But again, let me check the code and see. We can see that it's trying to turn and then locate that robot, and then it's going there. Okay. We will not be able to do the stop thing. I can see 20 minutes I give is like up, or it's almost 5. So we're going to stop here. We're going to stop here. We're going to stop here. So basically, I can like iterate what we just did. What we did is that we have 2 robots. We spawned both of them. The second robot was spawned at a different location. And I also want to say this again. The ROS2 course is still available. You can check our website. You can register if you want to learn how to do robot operating system 2, which I'm going to do a short demonstration. Okay, so it's a very nice course where you will learn how to program in Python. You will learn how to program in C++, and you will learn how to build robot solutions with those programming languages. Yeah. Hello, Yeti.
Hi, I'm here. Do you need something from me?
Yeah, I want to stop the stuff here, this part here.
Oh, okay. Yeah, I followed.
Yeah.
Because I was looking at time. I was cognizant of the time. But
Yeah.
you can go ahead and show the demo. Yeah, there are a few announcements for people who are still willing to wait. Because I mean we didn't finish. So if you're wondering like what's next, what happens, are we going to have another session or something, you can just hold on. But I'll allow Lincoln, to finish his part, and yeah.
Okay. Okay. So this is all about PyBullet. Now, there's another thing we quickly want to do. I don't know. I recently had an issue with my computer. So let me just quickly set up something, and I'm going to launch it. So while I'm doing that, I still want to remind you of the Robot Operating System 2 for Beginners course. If you are new to robotics, you want to start to learn how to program robotics, then that course is for you. So I want to launch something now, but I need to set it up properly.
You can go ahead. So I'm sharing a link in the chat. Like we said, let me just quickly make this announcement while Recon is trying to set up. So the first thing is that like what's next for you. If you've not joined the Slack community, please do that. If you have never heard from us at all, I'm wondering how you are here because I'm assuming you've heard of us from us through the newsletter, but it looks like maybe some people were still not able to get through the newsletter. So if you're here and you've never received any newsletter from us, please, just put an indication, or you can just send an email to reflectrobotics@gmail.com. So I'm putting that up in the chat. You can just send an email to us at reflectrobotics@gmail.com. That is if you are not receiving newsletters from us. But first of all, before you do that, check your spam, check your promotions, check all of those places that it could have escaped you, so that you're sure that you are, you're getting it from us and not raising a false alarm. The other thing is that I'm going to use Lincoln because of his keyboard. The other thing is that you could also so join the Slack community, because what we're trying to do is to build a community of learners when it comes to like robotics, not just in Nigeria, for instance, worldwide. You barely have a community where people can actually bring problems that they are facing or whatever, and they can get a community who can, you know, help them with their issues. So it's like creating like a Stack Overflow, but for developers. But this time around, we just tried to build this community for, you know, robotics engineers and people interested in robotics generally. So feel free to join the Slack group and look out for the RR community group on Slack. Very soon, when we grow large, we would move to maybe a discourse. That's something still in the pipeline. We are not yet sure that. So just bear that in mind. The other thing that I was going to mention is while we are waiting for Lincoln, please can you all click this link and give us a feedback? We can't know if we're doing a good job or a terrible job today. So please feel free to, not feel free, actually, I'm begging. I'm literally begging. If I can need, I'll do that. Maybe I should share my video so you see me. I'm pleading, please fill the form. We really need your feedback because we are planning to have another webinar next month. So please, we need the feedback. This is our first webinar. We may have made mistakes. Yes, we know we are not perfect, but please fill the form. Let us know what you think. Let us know how we can improve. Let us know if you felt overwhelmed. I personally felt like you guys were overwhelmed. So let us know if something like this should be divided into like 10 classes, you know, and not one, or you think it should, be spread across, or this is fine for you. Just let us know through the, so just click the link, it's in the chat box. Many of you have also asked, will this be replayed? Yes, it will be replayed. You will get like a recording. We'll put this on our YouTube channel. If you've not subscribed, well, I don't know what to say. You should definitely subscribe, because for every of our monthly webinars, which we'll be having, as frequently as we can, we're going to take everything to YouTube. So we are making it publicly, accessible. So do check out our YouTube channel. It's Reflect Robotics, of course, and you would maybe before Monday, I don't want to promise today, but before Monday, this would actually go up on the channel. So watch out for that. And if you would like to volunteer with us, you can also send an email to us, reflectrobotics@gmail.com. For now, is everything every email, everything that you've received, we have like a very, very small team, mostly, of course, I and Lekon try to, oversee, but other people who have joined are literally the newsletters you receive, the graphics design. There are people who are actually, not getting nothing from us, and they're just, doing this for us as a passion. So if you would like to join as a volunteer to, host sessions with Lekon, for instance, because it's not every time that I have to be there. I mean, the monthly session is for you guys, it's for you to learn more. We'll also have like polls for people to vote what they would like to learn, and we use the highest number of topics, to know how we can prepare content for the webinars. So please, yeah, please try to volunteer if you can. If you have the time, please volunteer with us. We really want that. If you also think you can teach, please volunteer with us. We're looking forward to that as well. I don't know if Lekon is ready. Yeah, so like I said, Rizama, it's just look for Reflect Robotics. Just look for Reflect Robotics on YouTube channel. Lekon, are you able to unmute?
Yes, I just do that now. Thank you.
Are you ready? No.
This thing is not.
It's not. It's all right. It's all right. You can, when you're able to do the demo, we can upload it on our YouTube channel. for people to see.
Yeah.
If you're not able to do it on this call, that's all right. I mean, technology is technology. Sometimes it's, I'm sure, or every one of us know that, you know, sometimes things misbehave. Is there anything else you want to say? Oh yes, lastly, like you heard Lekon repeated, we have premium courses, which are like the paid courses. And one of the very first course that we have is the ROS2 for beginners. Why ROS2? Because that's like the, people use PyBullet, like I use PyBullet for instance, but ROS2 is even much more used in the robotic community, in academic, especially even in companies like standard industrial companies. ROS2 is widely used for in the robotic space, although PyBullet is used, but ROS2 is heavily used. So we have a premium course on that. If you check the website, you're going to see. So for anyone who is interested, please check that out. Unlike other online courses that you take that you're left by yourself, ours is a mix of hybrid. We understand that sometimes you may be taking this a particular class, and for instance there's something that you don't understand, so we have another part of, when you pay for the course, what comes with it is that you also have access to the instructor to ask questions. That is like a one-on-one session where you can ask questions on things that you don't understand, or things that you need clarifications on, or you're trying to set up and there's just some error and all of that. So that comes with the course. It's not like, oh, we just saw the course and then we let you go by yourself to finish it. We have that, you know, that one-on-one with the instructor in place with, you know, with the course. So do check the website if you're interested in that. Yeah, it's very useful because we've had like a pilot student who took that. Yeah, they were like just hailing Liko and like, you did a good job, you know, explaining this concept to us. So I'm going to check the form. I have 11 people here, minus I and Liko, I have 9 people. So I'm actually going to check the form to verify that, you know, we've please done what we should do by, so I'm going to check the response. It's very easy, like it's straightforward. We didn't make it like all of those. We have just 2 responses. No, guys, you can do better. You can do better. You can actually do better. We have just 2 responses. I'm going to keep refreshing. We have 9 people on this. So at least we should have more than half of people who are here fill the form. At least we should have 5 people on that. We need that feedback. We can't walk in blindly to organize more webinars if we don't get feedback from you guys. Like it doesn't make any sense at all. So please feel it takes literally less than 3 minutes, not 10 minutes, 3 minutes, because you're just clicking, you know, yes, no, and all of that. So please fill the form. We really need that response. I can share again. Thank you. Okay, the link to the course, I'm going to do that now. Yeah, actually, I should have done that. So the link to the course, I'm going to put it in the chat section. Is there any link to the form? Oh, I shared it. Okay, let me share it again. Let me share it again. I actually thought I had shared it earlier, but I'm going to do it again. Okay, here you go. Samuel, the form is below, and Yanulu at the link to the ROS2 courses also in the chat section. You're welcome. All right, so Lekon, do you figure it out? If not, you know, we've actually spent more than.
I couldn't figure it out. I
Alright,
think I tampered with some files.
okay, no pressure, no pressure. It's all right. When you do, you can just do a short video and we'll send this across the newsletter. Don't worry. So you have no problem. We'll send this. So I have 4 responses here. Can I have one more, please? There's just that one person that don't want to fill this form. Please, can you fill it? Please, let's just have at least 5 people fill this form. So I have just 4 responses. Can we have one more person fill it? It's really straightforward. Guys, please do it. Please. Don't be shy. Please do it so that we can say goodbye. So I'm going to stop the recording now since Lucon's trying to figure that out.